Hello everyone, my name is Lior Korobeinikov, founder and current team manager of Tel Aviv University's TAUver IL. We are beyond excited to compete at ERC 2026 with our rover, Exodus. This year, the team is composed of around 50 members from various degrees, ranging from engineering to applied sciences and health sciences. To work as efficiently as possible, we have divided the work between 10 subdivisions and assigned clear roles to everyone. Each subdivision is composed of a team lead and 2 to 5 team members, with a member from the industry to help with advice and guidance if needed. Above the subdivision team leads, we have 5 system engineers, each dedicated to several different divisions and the integration of the systems as a whole. In the management side of things, we have several key members who partake in different roles such as marketing, industry relations, logistics, and more.
TAUver IL is a passion project set up and run entirely by Tel Aviv University students as a way to grow the future generation of engineers and provide them hands-on experience during their degree. It was born out of pure love for the space industry and a passion to promote it in Israeli academia. Our close relations with both the industry and academia provide our students a way to launch their future careers with built-in knowledge. We chose the ERC specifically as we aim high. There hasn't been an Israeli team in the competition of 2026, and we plan on changing that by being part of the most prestigious rover building competition out there. We are a relatively new team. As a new team, we are also very excited by the prospect of meeting more experienced teams in the Mars yard and getting to know their ways of thinking and working.
The rover was designed with a modular architecture based on a main chassis platform with replaceable modules, where each module is a subsystem by itself. This allows us to change configurations between missions and also upgrade the future systems without redesigning the entire rover.
Our team is responsible for 3 critical pillars: the chassis, the mobility system, and the integration of the other subsystem into a fully functional rover. To achieve this, every single design choice was driven by weight optimization and terrain traversability. For the chassis, we selected aluminum as our primary structural material. The strength to weight ratio of aluminum is perfect to shave off critical kilogram, and it has high corrosion resistance, so to harsh environments. For mobility, we chose to combine custom airless wheels with air shock absorbers. Eliminating pneumatic tires reduces the risks of punctures or pressure loss on sharp or abrasive rocks while allowing the thread to compliantly deform and maximize ground traction. The shock absorbers isolate the rover from harsh impacts and keep our scientific payloads stable over uneven terrain. For the steering, we implemented an independent 4-corner directional system. It allows for a tight turning radius, crabbing maneuvers, and unparalleled agility navigating tight boulder fields. For the actuation, we use IP-rated waterproof motors. This guarantees that fine planetary dust and moisture cannot penetrate drivetrains, ensuring total system reliability under any environmental conditions.
This year, our primary objective was to design and develop the rover's complete electrical architecture with a strong emphasis on modularity and power optimization. The rover is powered by a custom 48-volt lithium-ion battery alongside a power distribution unit and battery management system capable of supporting high current subsystems under demanding operating conditions. To enable reliable battery monitoring and data acquisition, we integrated a CAN bus communication interface into the battery management system, allowing real-time monitoring of critical parameters such as voltage, current, temperature, and overall battery health throughout operation. For safety, we designed the system with 2 normally closed emergency stop buttons, allowing immediate power cutoff from multiple access points. We also developed a signaling system using 3 dedicated indicator lights to display different rover operational states.
Our team is responsible for developing the rover's autonomous capabilities, including localization, perception, and path planning to ensure mission execution without manual intervention. We are currently implementing a ZZZ camera setup to generate real-time point clouds for advanced environmental mapping. A key focus of our work is the direct integration of this 3D sensor data into the ROS2 COSMAP framework. By synchronizing these camera feeds for a real-time obstacle detection and avoidance, we are building a seamless connection between computer vision and autonomous navigation, ensuring safe and efficient movement in complex terrain.
The communication team is responsible for maintaining stable and continuous communication between the rover, the drone, and the ground control station. We operate across three frequencies band: 433 MHz, 2.4 GHz, and 5 GHz. During mission operations, telemetry data and emergency commands are transmitted over the 433 MHz link, while video streams, sensor data, and motion control commands are transmitted over the 2.4 GHz and the 5 GHz links.
Our drone is a custom quadcopter powered by a reliable dual 3S LiPo battery setup, including 4 carbon arms and 2 carbon landing pads. For flight control, it utilizes a PixarCube Orange Plus flight controller running PX4 firmware, which seamlessly enables both automatic takeoff and precision landing. The drone can move freely in all directions and achieves highly stable hovering using PX4's position mode. Flight telemetry is continuously monitored through the Q ground control application. This provides a unified interface that perfectly bridges our ground station computer with the RC inputs.
Safety is deeply integrated into our system architecture. A strict virtual geofence is enabled to constrain the flight area. In events such as data link loss, the drone can autonomously execute a return or land sequence. Additionally, to maximize on-site safety, a physical safety switch is mounted directly on the drone's body, providing an immediate hardware-level cutoff. Above all, our system guarantees that the operator can immediately switch to manual flight via a dedicated RC control switch whenever necessary. A Raspberry Pi flight computer integrated with a camera will allow the drone to execute fully autonomous flights from takeoff to landing. This system will rely on advanced image processing for real-time object detection and spatial localization.
Our role in the Mars mission is to collect a subsurface sample of at least 100 grams that reaches a depth of at least 30 centimeters. The system contains an Archimedes screw that collects the sand into the onboard container. The screw is lowered to the surface using a NEMA stepper motor and a lead screw. Both the DC and stepper motors have their own respective drivers to ensure that we stay in control of the drilling process in its entirety. The brain of our system is a TAUver 4.1 processing board along with drivers, 2 load cells to weigh our sample and to ensure that it's sufficient, a laser distance sensor to certify we start drilling at the correct height, and a camera to document before and after the drilling process.
Our mechanical manipulator is designed to support the rover in several ERC mission requirements, with a main focus on the sign task while also preparing for the maintenance task and the probing task. The manipulator has 5 degrees of freedom, which gives us a good balance between reach, flexibility, and mechanical simplicity. We designed it to be lightweight, reliable, and easy to maintain in field conditions. Another important design choice was to use only 2 types of motors across the manipulator. One of these motor types is also used by the mobility team for the rover wheels, which improves redundancy, simplifies spare part management, and makes maintenance easier during the competition.
As the control team lead, I was responsible for both driving control and robotic arm control systems. The rover uses an NVIDIA Jetson computer for computing the control of the driving and steering system, with Rust-based software architecture and a CAN bus communication with the motors. The operator controls the rover using a joystick for precise and intuitive driving. For the robotic arm, we use a dedicated NVIDIA Jetson computer responsible for the arm and drilling systems. The system controls 14 motors in addition to the drilling motors through ROS and CAN bus communication. We also use MoveIt for inverse kinematics and motion planning. The arm can operate manually with joystick or perform semi-autonomous tasks using camera-based image processing for science and maintenance operations while maintaining smooth and precise movement.
The role of the science team is to design, operate, and interpret the scientific systems on the rover in order to investigate both the Martian environment and the samples collected during the mission. The science system is responsible for acquiring, storing, and analyzing multiple types of samples. These include surface regolith and rock collected by the mechanical arm, as well as subsurface material extracted by the drill module. For the AstroBio challenge, we will collect and analyze a liquid sample to simulate the chemical analysis under Martian mission constraints. Once the samples are secured, we perform a series of quantitative measurements. Solid samples are weighed to determine mass consistency and material properties, while liquid samples undergo chemical analysis such as pH measurement.
In addition to sample analysis, the science team continuously monitors environmental conditions within the Mars yard. Our sensor suite measures parameters such as wind speed, humidity, methane concentration, CO2 level, and additional atmospheric indicators relevant to the planetary science and mission safety. All sensor data is logged and analyzed, and then used to validate or refute our hypothesis in the science planning report.